Okay, welcome everyone. I know it's a little bit of a trip right after our keynotes that we just had. I'm sure more people will be trickling in as things wrap up, and welcome to all those that are online as well. So we're going to be doing a great session ahead of us, talking about manufacturing process optimization, cloud to edge AI-driven solutions. And with us today, we have Vamsi Krishna Bupasamudram that's here with us. Oh, look at that. Standing ovation. But no, very good. Thank you for clapping. And thrilled to have him here. He's an AI consulting leader, 14 plus years of experience in this space. And without further ado, I'll pass it over to him. Questions we'll do at the end. And come on up. Let's give a round of applause, please.
Thank you. Thank you very much. Okay. Can everybody hear me? All right. Thank you. Very warm welcome. Thanks very much for being here. I'm obviously here representing Tredence. I'll jump in, right? Like I said, probably questions at the end. Please feel free to reach out both the last few minutes as well as at our respective booths in the manufacturing lounge. Happy to discuss more, right? Let me jump right in. Probably a lot of you might not know Tredence. I'll take a minute to talk about who Tredence is and what we do, right? We've been in this, working in the AI consulting space for about 9 years now, right? We work with many large Fortune 500 customers, right, across multiple verticals, right? The biggest thing that probably we're proud of is the NPS score that you see out there, right? Which is basically customers saying they love to work with us, right? And just so you guys know, we love to work with Databricks, right? That's the reason a lot of our solutions are based on Databricks, especially the AI-driven ones. And I'll walk you through what we're doing there and use a use case to illustrate. And hopefully, all of you have some takeaways from this. Yeah. So let me set some context first, because we're talking about manufacturing here and smart manufacturing. And there are very specific ways in which companies are leveraging the Industry 4.0 and related solutions, right? If you look at what's happening today, there are 3 key areas, right, where customers are trying to juggle their priorities, right? One is there are a lot of customer demands, not just about the quality, but the cost and price as well, right? And what they're balancing this with is actually a lot of capital investment on their equipments. A lot of it is old equipments. And all this while they face a lot of regulatory and community scrutiny over their energy and carbon footprints. Many a time, these are conflicting demands, right? And the need to balance them means a typical operational efficiency and cost saving is not a sufficient enough paradigm on which to base your manufacturing operations, right? And that's where you need a few different things to be put in place and drive your manufacturing itself, right? One is when you're doing or trying to integrate AI into your manufacturing operations, this can't be something that happens as an afterthought or something that takes, say, a few minutes to reach your plants, right? The insights, be it predictive, prescriptive, or even descriptive for that matter, has to be available in a matter of seconds or minutes at the max, right? The second is it's not always possible to stream your insights from the cloud into your manufacturing plants itself for a couple of reasons. One is your manufacturing plants might be located in remote areas, which means they might not have the most reliable network connectivity. And even when they have, cybersecurity concerns mean that you would rather have solutions running within the plants without having any kind of dependency on the internet, right? And while you're doing all of this, you just don't want to provide insights, but try and integrate these solutions into the PLCs and the monitoring systems in the plant itself to the extent possible and make the adoption itself very easy, right? So any AI solution that you build, typically you would want to solve for all these 3 kind of problems so that beyond the Industry 3.0 and the automation that it provided, you're able to enable the intelligent automation that AI can further build on top of that, right? And that's basically what AI is providing today, right? Now, what's the way forward, right? What do you do, right? There are some key challenges that you need to think of. One is, I'm assuming if there are some manufacturing customers here that in the plants, you're probably missing people with the right technology skills, right? Even when you have them, you have the external network and you have your internal teams, and implementing the AI models that are built on the cloud, on the edge itself, is not very easy, right? And when you do it, right, even when you're doing it, you need to continuously monitor the performance of these models and whether they are being adopted by your plant machine operators and your engineers, and have a feedback loop, right? That means what you need is certain digital solutions that can bridge the gap, right? Bridge is the right word here because the cloud and the edge are almost two disparate ecosystems, and you need a bridge to actually make sure that the promise of AI on the cloud is actually available in the plants on the edge, right? And that's the reason any solution that you build, right, something that needs to have these three things. It needs to make AI democratized, right? Something that the plant folks can understand, at least the digital champions within the plant can understand. It needs to be integrated in the sense that the pipelines in the cloud and the edge need to be synced and not something that can be manually updated, because again, your insights need to be real time, right? And the third is the monitoring itself needs to happen with a ops approach, right? All of you probably have attended a lot of sessions about ML ops across the last couple of days. And if you extend that to the edge, it becomes edge ML ops and edge AI ops, right? And that's basically what you need to implement in each of your digital solutions, right? What you see here is a reference architecture, which probably many of you might be using to develop and deliver many of these solutions, right? On the left, you see your various sensors and process-related data coming in. Your edge infrastructure, it could be on Azure, AWS, or something else, right? That's actually capturing the data and taking it to the cloud. In the cloud, you have all the services where you build the models and implement them or productionize them. And then, of course, you bring those production models back onto the edge and deploy them there, right? And again, on the edge, you might have various types of compute devices. Your compute devices might be server-grade infrastructure in the plants, but it could also be very small form factor devices, which means your models and the insights need to be really, really compressed, right, in order to be actually useful and deployable on those devices very close to the machinery. Now, this is not something probably that you implement from day one, right? But rather, this is a journey, right? And this is one view of the journey itself. I'm having trouble with the monitor, but yeah, okay, sorry. This is one view of the journey. I'm not sure if you've seen something like this before. I find it a very useful reference to how a lot of our customers traverse the smart manufacturing journey, starting from having the right visibility, right, and the right operational insights to actually going to more predictive and prescriptive right, zones itself. Now, you can also think of it as the first two steps here as being the BI and the discovery of your plant operations and what's going right and what's going wrong. And the upper part of it is where the AI really comes into the picture, right? And the use case that I'm going to talk about today is one of those examples where using which companies can actually get started on their smart manufacturing journey, leveraging not just descriptive, but predictive analytics. Right? So let me go to the use case, and I'm hoping that many of you will relate to it, and if not, we can always chat about how that might relate to your particular environments, right? But the use case I'm talking about here today is about a process industry, a metal manufacturing shop floor, right? This is not the upstream metal manufacturing I'm talking about, where you have your ore and extraction and actually having the, the pure metal itself, but rather, once you have the metal extracted, how do you use that to manufacture specific products, right? Now, in this use case, our customer was a rolling mill, had a rolling mill set up, right? One of the biggest aluminium product manufacturers in the world. And their problem was that they have a lot of rolling mills. Each of those rolling mills, for people who are aware, runs into hundreds of millions of dollars in terms of cost. They're huge machines, which means any kind of downtime or productivity loss is very, very costly, right? So, and the whole process itself starts with multiple mills and ends with a cold rolling mill, right? And as they go through this process, there are a few different defects that they started noticing, right? That could be certain wrinkles on the final aluminium coils that they were getting at the end. There were certain pinholes that were getting created, right? Or certain changes or disturbances in the profile of those coils at the edges. Now, there are multiple reasons why this can happen, right? But the idea is not to necessarily always go after solving the engineering part of this, but rather, the idea was, can you really tinker with the last phase of this process, which is the cold rolling mill operations, such that whatever happened before this, you can correct for in the final stage. Now, there were always two ways to do this, right? One is you could have say a computer vision kind of a model after the cold rolling mill and say, hey, let me look at where the defect is happening. And whenever that is happening, I can immediately stop the machine, cut the coil and throw it out or recycle it, and then start my machine again, right? A couple of problems with that. One is it's a post-mortem, which means that you're always behind the curve, and all you can do is remove take care of what's already done, but you can't really prevent it, right? And the second is this is likely to lead to a lot more stoppages, right, than you really want to, right? That's the reason the idea that we came up with, that we implemented, said, hey, don't worry about computer vision for now, right? But let's see if we can look at the operational data for all the pre-processing that has happened, right? And then say, can I figure out the right way to operate the cold rolling mill such that you reduce the number of stoppages that can happen and hence the amount of scrap that you generate, right? The amount of scrap generated, apart from the loss in terms of either selling a downgraded product, is also about the productivity loss and also about carbon footprint, because you're using that much more energy, right, in terms of actually recreating that product itself, right? So that's basically what that meant was, this was a continuous process, right? So what that meant was this is not something where the machine could stand still waiting for somebody to say what is the right way to operate the cold rolling mill for every cycle. Between two mini cycles, all they had was a couple of minutes of gap, right? And within those 2 minutes of gap, they needed an analytics engine which could say, hey, let me look at all the pre-processing that has happened, and then say, within those 2 minutes, based on everything that's happened, now I tell you, what are the right parameter settings that I input into the final cold rolling mill such that my outcome is as best as can be achieved, right? So remember that word, that's the 2 minutes is the most critical thing here, and that 2 minutes could be sometimes 1 minute, could be a few seconds, and the model that you build, as well as the way you miniaturize the model, the way you deploy the model is all dependent on the amount of latency that is applicable to your particular use case, right? And of course, the amount of infrastructure that you have in the plant, right? So that's the reason this is something that we had to deploy within the plant servers or on the plant servers, right? What we did not have to do in this case was deploy the models on the PLC of the machine itself, right? That's also a use case we're taking up, but that would mean further miniaturization of this model. This is probably slightly less complex in terms of use case because we still have access to the plant server infrastructure to run the prediction engine of the model itself, right? Doesn't mean it's not challenging, but it just makes life a little bit more easier in terms of being able to deploy, right? What you see here now is the architecture that we used, right? As you can see, it's Azure and Databricks, right? But let me take you through it a little bit, right? At the right bottom, what you see here is the rolling mill, the one that you see, the number one. From the rolling mill, right? And that is not the, right? And from the rolling mill, as the rolling mill rotates, you have the data getting generated every second, right? In terms of what's happening, and that's getting fed to the plant historian, which is a time series database within the plant, right? And from that time series database, and not just from the cold rolling mill, but the upstream mills as well, all the data is going through the server to the cloud, right? Is going to Azure, and then sitting in Delta Lake. Within Delta Lake, we're using Databricks to build the model, right? In this case, it was an XGBoost model, but probably you could use a few other approaches. But the idea was, can I use the various features? In this case, we were dealing with 2,500 features. Please don't ask me what 2,500 features are, right? But you can think of any and all transformations of multiple data points of the cold rolling mill, including the torque, the RPM, the tilt and bend, and many such metrics, right? And when you combine all of this, what we were trying to predict was what parameters, especially in terms of the tilt and bend of the rolling mills, would you actually run that cold rolling mill at, such that the outcome was something that was very close to what was required and free of defects, right? Before we implemented the solution, about 10% of the cycles had to be stopped midway and then restarted with the correct settings, right? That was the problem we were dealing with. Now, after we built this model, of course, like I said, this is built on Azure and Databricks, and we use the Databricks feature store, right, to actually make sure that all these feature engineering pipelines are automated and are present, right? Not just that, once we deployed these models on the plant infrastructure, right, we actually created a feature store as well on the edge, right? This is super important because the feature store on the edge is something that is helping us make sure that all the potential pre-processed features are available to be used as soon as the next cycle has to start, right? So the minute the hot finishing mill stopped and finished the processing, there was a 2-minute cycle. The predictive engine or of the model that we deployed on the edge is something that starts to run as soon as the hot finishing mill finishes, and then the features from there go to the edge feature store, and within 60 seconds, I mean, we have hit 60 seconds now. Our idea is, we're still working on it, improve it further. The idea is to take it down below half a minute, right? Because the minute we do that, it opens up another range of possibilities of the number of use cases that you can unlock in other parts of the plant as well, right? So that within those 30, 40 seconds, you have the predictions of what the tilt and bend parameters need to be available to the operator. Now, the last point probably to mention is the change management itself, right? So a lot of the manufacturers struggle to implement the solutions, but implementation is probably not their biggest problem, right? The problem many times is, how do I get my plant operators or the machine operators to actually adopt these solutions, right? And that is where we spent a lot of time. So what we did in this case is, once we built the solution and the prescriptive analytics started kicking in, the machine parameters was something that we started putting into the HMI of the machine itself. Now, there are two ways to do this, right? So one is, you can integrate this with the PLC itself, right? And probably pretty soon we're going to be doing that. But before that, what you need to do is, you need to get the confidence of the machine operators that you're going to give them the right results. And how do you do that? This is one example, right? Where we said, we'll show you what our model is prescribing as the right machine parameters on your HMI, right? The human machine interface. And hopefully you like what you see, right? And if you like what you see, then you say yes. Otherwise you say no, and you actually enter something else manually, right? You have the 2-minute cycle, you go ahead and enter something manually. And for a long time, the operators start doing this. And as you do this, you have your input or the feedback loop that's going from the operators back to the cloud as an input to your model, right? And that's basically what your feedback loop is, continuously retraining the model till the time where your operators are saying, hey, I'm confident that your prescriptions and predictions are right. I'm going to be using them. And now, as and when this matures over a period of time, right, this is something that they will say, hey, okay, I don't need to make this decision every time manually. What I'm going to do is, I'll open a port, I'll let you connect to the PLC, and you can feel free to just directly give the recommendations or the inputs to the PLC itself, and the whole process is automated. And that's the first step. Now, once you've done this for one machine, for one use case, of course, right, you can actually it's very repeatable, right? And especially if it's within the same plant, there are potentially hundreds of use cases, and something that you can scale very quickly, both within plants and across plants, right? Now, this is just one example, right? Another use case with the same customer was around, hey, how do I optimize the energy consumption of my blowers, right? And that's even more real-time optimization, where we're actually working to implement the model results onto the PLC itself, because the latency requirement there is, say, less than 5 seconds, because the lower the latency, the higher the energy savings, right? And you can expand these use cases by leaps and bounds, of course. Now, as we did this, right, just wanted to spend a few minutes on what the takeaways could be, right? The first and biggest problem that we addressed when we did this was reducing the number of stoppages itself. Like I said, right, each of these, where do I go? Okay, so each of these machines, right, I know they look very small and cute on the screen here, right, but they're huge, right? And every few minutes of stoppage that you can reduce here is a very, very big number, right? So they were literally looking at tens of millions of dollars saved for every, say, half an hour of production that we were able to save with this, right? And the problem was, imagine it starts giving you the coil with the wrong profile. What do you have to do? You stop the machine, right? There's somebody who comes in with a saw, they cut the coil, right? They have to remove it, and that coil itself is either you put back into your smelter and reuse it, right? Or you have to just throw it away and sell it, like I said before, right? And once you do that, somebody else has to come in and say, hey, now what metrics do I input? What parameters do I input? And they have to restart the machine, right? And in the meanwhile, your upstream WIP inventory is also getting stacked up, right? There's a whole chain reaction to the amount of bottleneck that's getting created, right? So imagine every half an hour of production loss resulting in at least $40 to $50 million of losses, right? Huge. And this is a company that's supplying to a lot of the automobile companies, a lot of the beverage can manufacturers, right? Sheet metals, battery casings that are relevant for EV, cars, right? And you know that EV car manufacturing is one of those industries which is highly supply constrained, right? So, and that's caused by these kind of stoppages many times of the available capacity itself, right? And that's the reason what you saw there was the number of stoppages that you can reduce. Forget the scheduled stoppages for predictive maintenance. Of course, that's a whole different use case. But the number of stoppages that you reduce in terms of the unscheduled stoppages itself can be a huge benefit. Okay. The other one is the amount of time it takes to do your quality control and quality assurance, right? Of course, different companies follow different levels in thoroughness in terms of QC and QA, right? And you can always have your computer vision models, like I said, to say, hey, whether my quality assurance is top notch or not, right? But it gives you, when you have these kind of models in place, it gives you the confidence to say, I can probably get away with less than 100% quality checks, right? I know that if in a batch that I've taken, I'm always going to get less than 1% of defects. I know what I'm going to promise to my customer. I know the amount of effort and energy that I need to invest to achieve a certain level of quality assurance, right? That's the second very important benefit of this. And the second one, which is always not very obvious but super important here, is the energy footprint, right? We're working on multiple solutions in the sustainability space, and energy footprint reduction is right up there, right? And it's not just linked to operational efficiency and not just about the electricity direct consumption that's happening in the plant, but remember that every time the wrong profile of the coil gets generated, what you're seeing is there's an increase in the amount of raw material processing that has to happen. And of course, that's fed by still a lot of fossil fuels and the increase in the emissions that's there itself, right? And of course, that results in carbon footprint increase, and et cetera, right? Now, when you have any of these implementations, right? Something that's super important is how do you really engage with your customer, with the plant, and with your user itself. And many a time, all these three are very different, right? So typically in my experience, there are 3 personas or 4 personas, right? And when you implement these kind of solutions, you have your central data science and data engineering teams. Within the plant, you have your plant digital teams. Then you have your machine operators, right? These are the three core ones. And now each of them have to work together to build and implement these solutions, right? And each of them come with different skill sets and different priorities. Now, and that's the reason it's super important to choose at the very beginning both the use case that you're going to start off with as well as the plant that you're going to start off with, right? So one of our customers has about 150 plants all over the world, right? Now, the way we implement it is in cohorts, right? So we started with just 1 or 2 plants to begin with, said, hey, these plants have a great open cultural compatibility with digital solutions, right? They have the basic automation in place that comes with Industry 3.0, right? And there are a lot of problems to solve, right? So you can use this kind of a framework to say, hey, where do I start, right? And how do I start implementing my solution? You create that first few successful use cases within that plant, right, in the first 6 months. And once you've done that, over a period of time, what you can do is scale not just the same use case across multiple plants, but also multiple use cases within the same plant as well. And the good thing is, all the infrastructure that you see here, right, that you saw in this architecture is largely reusable, right? Both the architecture as well as a lot of these components and even services that you build are very much reusable and in many ways automatable itself. So once you've started on that initial journey and built this out for a few use cases, then typically what we've seen is 2 months to do a pilot, right? And 3 months to start implementing it across plants, right? That's what you could do. And in fact, to speed this up is why we have actually developed one solution. People who are interested, please come by the booth, something that we refer to as high tea, right? That's because we want to give the plant operators a little bit of a rest in the evenings. But the idea is, how do you make the deployment of some of these models very, very smooth and seamless on the edge, right? And that's where our focus is on in developing those capabilities for our customers. A lot of them in the cement, metal, glass, and other such process industries. And of course, all of those relevant for other industries as well, right? But I'll take a pause here. I can go back and forth, of course, if there's something else, but otherwise, I'll take a pause and I'm open for questions. Thank you. Hi, sorry.
Sorry if I missed it before during your presentation. Just wondering, when you are trying to get the data from the rolling mill, are you guys also connecting, for example, with the SCADA system?
With the SCADA system? Yeah. So depends on whether or not you have a historian. For example, in this case, we had a historian, right? So yeah, I'm on the right slide. So if you see here, the rolling mill, right? The PLC and SCADA systems are there, but the data is actually getting captured on the plant historian, which is a time series database. But if you did not have that, right, the historian is a quasi-edge device of sorts. So you could directly connect and take that to the cloud as well. But typically, you don't do it because of, you don't want to open up the control systems to the cloud and to other, say, cyber attacks and all of that. So historian is normally there. But if you wanted to, put some measures in place, and you could very much take that directly as well.
Yeah, because that's my follow-up question is, as what you said is, if you are trying to connect that directly with the SCADA system, usually it would be residing like a different environment, like an OT environment as opposed to IT environment. And also possibly it may not that efficient, right, to connect directly with the SCADA system. Yeah,
even though it's definitely in the OT layer, but for example, when you use an architecture like this, you have your Azure IoT Edge that is present or installed in the plant servers, and you can use that as a right conduit to get the data and push it out. But like you said, right, typically more for security reasons, and the fact that it could, even sometimes if it's not handled correctly, you might even end up having certain accidents per se if the machines are not controlled properly. You normally try to have some kind of almost like an air gapping between your OT and IT systems to prevent those kind of problems.
Thank you.
Thanks, Vamsi, for the presentation. That was very interesting approach. So it seems like a pretty complicated process that you're trying to optimize with like
Did you say complicated?
Complicated, right?
Okay.
Yeah, with like over 5,000, parameters, variables and all that. So I'm wondering if you had enough historical data to train your model with, or do you have to do some kind of augmentation, like using simulators to create more data, increase the coverage and all that?
Right. Sorry, the mic is a little bit blurred, but you meant if you didn't have enough data, could you simulate the data? Is that what you meant?
Wondering if you had enough historical, like true data to train your model on, or you have to kind of do some augmentation using simulator or other approach.
You could use a simulator. I mean, it definitely never reflects the true data characteristics that you would see, right? I use simulators as well when I'm trying to do my internal POCs, right? Before we're actually going to the client and implementing certain solutions. You could do that. It doesn't always reflect all the data characteristics. For example, one of the biggest problems even here was, within the historian, I mean, every software has bugs, right? So, and a lot of these sensors are all analog to digital converters at the end of the day, right? In terms of how the signal happens. So you just start getting some null values in between, right? And you have to know whether the null value was because the machine was off, not working, or it's just a problem with the sensor, right? And many such scenarios, right, that could happen, which you will not discover when you simulate, say, synthetic data within your environment, right? But nevertheless, you could probably build a 50 to 60% ready solution and then have your data quality as the core focus when you actually start implementing this. And the main focus is on, hey, let me make sure I get the data straight, right? We had a lot of data issues here, for example, right? I know we just spoke for about 20 minutes, but some of the problem was, hey, the features or the data that you're getting, is it for the whole coil length, right? Each of these coil rolls are about 5 kilometers in length, right? They keep rolling this way. Now, whenever there's a problem, they will cut, say, about 10 to 20 meters of coil, right? And even when there is no problem, they will cut 10 to 20 meters of coil for quality inspections, right? Now, you want to know whether the profile data in terms of thickness and the width and length and all of that, whether it is for the whole length of 5 kilometer length, or is it for 4.5 kilometers that got processed before, right? So each of these, say, data variations and patterns is something that you will see when you're actually working with very, very real data and real systems, right? So most likely, if you already have a pre-built solution of sorts that you're using, then most of your energy will go into just solving data quality issues. And once you've done that, what you might have to do is do some model rebuilding, right? In this case, we actually used AutoML kind of an approach such that we don't have to build a manual model every time there is an issue or there is some kind of drift in the model performance, right? And if you're using that, hopefully everything else but the data quality is sorted, then you could accelerate your development that ways, even when you don't have enough data.
Thank you for the presentation. I have two questions, and they're related. But the first is, I believe you mentioned that it was a Databricks XGBoost model that eventually came out. And I was wondering if the deployment process, if you use the ML flow kind of deployment methodology for like their stage and production releasing that you can track with ML flow. And then the second question connected to that is, did different machines ever have different models deployed to them? And how did you track those deployments to the actual edge machines, knowing which machines had which models on them at a given time?
Sorry, I didn't catch the first question around.
The first question was just, did you use the ML flow kind of deployment methodology for tagging a model as a staged release or a production release?
Mm-hmm. Yeah, ML flow, I'm sure it's part of the architecture somewhere. If it's
Okay.
if it's not, it is.
Okay.
Right? MLflow is definitely what we're using, right? Both for the versioning as well as mapping the right models to the right target assets in edge devices itself, right?
Okay.
That's very important. In fact, this was not just one model, right? So there were 4 different states in which the asset could be operating on, and each of those had 2 different versions, right? I'll not go into the details. So there were actually 8 different models and 8 different predictions that we were generating, right? Applicable under different scenarios, right?
Okay.
And that's something along with the model pipelines. And in fact, here, even the prediction engine on the edge actually had Spark pipelines, because we needed to have very low latency predictions, which meant we actually brought Spark, the power of Spark, onto the edge, which typically you don't do, but we needed to do that, right? And within that, again, because this was the first model within that plant, we didn't use Kubernetes, right? But technically, you could use Kubernetes when you have a lot of models applicable either to the same asset or even multiple models mapped to different assets that need to work in conjunction to actually orchestrate all the ML models together and the predictions accordingly.